Go.
Hello, my dear students. I want to do a quick video, so I'm going to talk real fast. If you need help or need to write down what I'm writing or write down what I'm saying, feel free to hit pause or rewind to hear it again. But I'm going to quickly do our lab discussion for our flame test lab because I'm ready to post another lab for next week after Thanksgiving, where we start to examine the group 1 and group 2 elements, the alkali metals and alkali earth metals from the periodic table and their properties. And one thing we'll do is flame test. We'll also look at some of their chemical properties and how they react. But right now, let's talk about our flame test, especially and specifically as it relates to atomic structure. And we will, if you remember, we did this lab, we wrote down some of our colors, and if you read through the lab, there's lots of good information in there. And what it wants us to do is record our colors and then refer back up to this table so that you can get the wavelength. Come on in over here and let me remind you of our equation where the velocity is equal to the wavelength times the frequency. In chemistry, we use the symbol c, which is a constant for the speed of light, lambda for wavelength, and we use this Greek letter nu, N-U, for frequency. And what we're going to do is take our wavelength, speed of light's a constant, 3 times 10 to the 10th centimeters per second, or 3 times 10 to the 8th meters per second, and we're going to calculate our frequency. Once we know that frequency, we can use that to calculate the energy. And you're going to see some important concepts, and that is, I'm just jumping ahead, that long wavelength light, if you have a bigger wavelength, you have a smaller frequency, because these are inversely proportional, because this is a constant. So if the wavelength goes up, the frequency has to go down. But the short wavelength light, the blues and the violets and the ultraviolets have a much higher frequency. They hit and impinge on a surface much more frequently and carry a lot more energy because they're hitting it more frequently. That's one way to look at it. And we're going to see that they are higher energy, and we can calculate that energy using Planck's equation. This is the same Planck named after, that the Max Planck Institute, the world famous research institute, is named after. And he not only has an equation, he has a constant, because in his equation, the energy is equal to the frequency times Planck's constant. And here's Planck's constant, 6.63 times 10 minus 34 joules per second. So we're going to do some simple math to do our calculations. So when I go down here, we were asked to record the colors and the flame intensity. But what we want to do is go, after we get our colors, go back up and look up what wavelength that was in that table, okay? So I just happen to have them written down in this one. And if I can make this bigger and get to this table where we want it, you can see barium chloride was pale green. That's a wavelength of 577 nanometers from the table. If I take the 577 nanometers here and I just do this, my frequency, nu, is equal to, I solve for nu, it's equal to the speed of light divided by the wavelength. And this is a constant, 3 times 10 to the 8th meters per second. And we'll get our wavelength. And the only problem is the wavelength given in that table is in nanometers. There's 10 to the 9th nanometers in a meter, okay? So we're going to have to do some calculations to get that. But if you go up there, barium chloride is pale green, and it's 577 nanometers. Calcium chloride is orange red, 622 nanometers. Copper chloride, blue green, 492 nanometers. Potassium chloride, lilac or purple, 426 nanometers. Lithium chloride, red at 701 nanometers. And sodium chloride gave us an orange color at 609 nanometers. You can see the flame intensities there, but I'm going to go down to our next table where we had to work out those frequencies. So that 577 nanometers, don't forget, they're 10 to the 9th nanometers, milli, micro, nano per meter. Okay? So we want to convert those values to meters, and then we will use that to solve the frequency. Okay? Let's pause the tape and we'll continue on in the next one.